All right, we're gonna make a video here doing a review of section 7.2, and I'll do another one for 7.3, which we covered right before spring break. So before we get into doing new material, we'll cover sort of the basics of what we have seen already, and this is what your homework that's due Tuesday is on. So hopefully you already sort of have this covered, but we'll have this video anyway, just in case. So the whole idea of the Laplace transform is that it's a function that operates on functions. Okay, so you input a function into the operator, and then it spits out a new function. And so there are a couple of ways to notate it. And the notation is really strange, and this whole concept is really strange, so we just sort of have to deal with it. So we have this Laplace operator. We use the curly braces, and then what we put in as the input to the function is some f of t, some function. And so what's really tricky and super important here is that the sort of variable, the independent variable of this little f function is t, okay? And then what we end up with after we do the Laplace transform is going to be some new function, big F, and that's going to be of a variable s, okay? So what ends up happening is that we're switching from like sort of the time domain or one sort of universe of in our variable t, and then ending up shifting it into a new universe with this variable s. And the reason that we do that is that we end up finding that some things, like some differential equations, end up being easier to deal with in the S space. And that's what we'll see sort of after we finish covering how you even use the Laplace transform in the first place. So the notation, back to the notation, we have the curly L here, and then the curly braces here. So sometimes you see it when you put your function on the inside there, and then sometimes you talk about this big F instead. And so those are sort of two different ways of talking about it. And you can tell that the big F is like the answer to a Laplace transform because it's a function of S, whereas the little f over on the left-hand side is a function of t, and so it lives in the, like, sort of the before world of the Laplace transform. Okay, so the first thing we're going to do is just give the definition, and we're not going to give any motivation for why this definition is a thing. It's just what it is, and we just have to be patient and wait until we've had a couple lectures to say, okay, this is actually a useful definition. But sort of all the properties that end up falling out from this give us clues to why this might end up being a useful definition. So we have a definition. Let f of t be a function on 0 to infinity. And then we define the Laplace transform of f is the function, capital F, defined by big F of s is equal to, just by definition, the integral from 0 to infinity e to the negative s t f of t dt. So the clear thing, or the thing to be clear on here, is that you're taking the integral with respect to t, and those are all the places that you have a t. Now, S is basically fixed. You're saying, well, what is big F if I plug in an S, and then you hold that S fixed in the integral, you compute the integral, and that's your answer. And because the integral has limits on it, the t's sort of end up going away because you plug in t equals 0, t equals infinity. So your answer is not going to have a t in it any longer. And so that's sort of how you get rid of the t and move into this S universe. Okay, so that's our definition. It looks maybe a little bit hard to think about, but we're not going to worry too much about it right now because we're going to do an example. And so there are actually tons and tons of examples in the book. Well, maybe not tons, but there's a couple examples in the book. And so in the book, there's examples of an exponential function and a sine function. I also did those in class. There are also videos on Khan Academy for computing both of those. And so I'm not going to do those again right now. You can go and watch the videos, which I'll link in the description. And you can go read the book and you can read your notes, blah, blah, blah. But I'm going to do another example that is from the book. This is example 4 in section 7.2. So let's write that. Oops, let's go back to black. Example 4, section 7.2. This is page 355. And we're given a function f of t equals 2 for t between 0 and 5. I think I did this one in class too. 0 if t is between 5 and 10, and e to the 4t for t greater than 10. Okay, so this is our function. It's a piecewise defined function. What does it look like? Sort of draw this a little bit over here. Let's see, that's ugly. I don't know how to erase. There we go. So we have some function that's defined on all positive t, and let's see, we've got 2 here, and now let's draw in green. Well, wait, we'll do black, and we'll do up to 5 and up to 10. So now if t is between 0 and 5, then we are at 2. And if t is between 5 and 10, then we're down here. And then for greater than 10, we get an exponential function, which basically looks like this. Okay, so that's what our function looks like. And what's nice about the Laplace transform, because it's defined as an integral, integrals are really easy to compute on piecewise defined functions because you can just kind of break it up. Because you can break up integrals and do all those pieces separately. So now what we want to do is compute the Laplace transform of f of t. And we're going to use the definition here. So the definition, as we have already written above, is the integral from 0 to infinity, e to the negative st, f of t, dt. Okay, so now we have to fill in f of t here, but what f of t is depends on where t is. So let's move up. So I guess I shouldn't move up too much. We want to be able to see the function. So this is going to equal the integral from 0 to 5 of e to the negative st times 2 dt plus the integral from 5 to 10 e to the negative st times 0 dt plus, oh, okay, got scaling issues, whatever. The integral from 10 to infinity of e to the negative st times e to the 4t dt. All right, so, okay, this 0, 1 is just going to be 0, so we can ignore that one. Now, the first integral here with the e to the negative st is reasonably easy because it's a definite integral. We don't have an infinity in there, so that's pretty easy to deal with. We can pull the 2 on the outside. And then if we do like a simple u substitution, we get 1 over s e to the negative st. We need a negative sign there. So negative 1 over s e to the negative st, and then we're going to evaluate this from t equals 0 to t equals 5. Okay. Plus, and then I'm just going to leave this, that stuff. And I'm going to worry about this first integral first. So remember, we're holding s fixed. So we're plugging in these limits, the integral limits for t. And so then that ends up with, we can plug in for t equals 0, and then that'll take care of the negative sign. So we're going to do 2 times bracket. Plugging in 0 makes e to the negative st be equal to 1. So we get 1 over s, that just stays, minus e to the negative 5s over s. Okay? Okay, so now let's try to move this some more. Now we can think about the indefinite integral with the infinity here. And what does it mean that we have infinity up in the top? Well, that means that we have a limit as big N goes to infinity, and then we can put finite limits on here, 10 to n. And now I can combine the two exponentials in the integrand, and I'm going to do that like this. E to the negative s minus 4 t dt. So you can convince yourself that what I just wrote, the integrand in there, is the same thing as the one in the line up above. And so the reason that I combined it like that is that now it basically looks like the same integrand we had in the first integral with the negative something times t, and our integration is going to follow exactly the same way. So let's jump down to the next line now, and we can, I don't know, we can simplify what we've got here just a smidge. Equals, I'm going to write it just the way the book has it. So we have 2 over s minus 2e to the negative 5s. 5 and s looks the same. Oh well. And now we can go back to our second integral. So we have a plus. We are not going to worry about the limit just yet. We're going to do limit as n goes to infinity and put some brackets. Now we'll do this integral just the same way as we did the first one. So we have negative 1 over s minus 4 times e to the negative s minus 4, s minus 4 t, and we're going to evaluate this from t equals 10 to t equals big N, close brackets, equals, look at that, we have the same thing. Those first two terms are the same, and then plus a limit as n goes to infinity. Now we can plug in t equals 10, so we get 1 over s minus 4 e to the negative 10 s minus 4 minus 1 over s minus 4 e to the negative n s minus 4. Now let me make an aside here. So let's come on over here and do another little example. Let's get a new color here. And let's say that we have some function with a negative sign, some function g of t. And we're evaluating this from t equals some limit a to t equals some other limit b. So of course this is going to equal negative g with b plugged in minus negative g with a plugged in. And so the positive signs or the negative signs cancel out and we get negative g of b minus or plus g of a, and then we can switch this around. This equals g of a minus g of b. So when you have a minus sign and you're evaluating some limits, you can get rid of the minus sign and then just switch the order of the limits. And so that's what we keep doing back over here. So let's get back into place now. All right. Keep going. We'll get, oops, let's switch back to black. We equal, those first two terms are the same. Then we have to calculate the limit inside the brackets, and the first term doesn't have an n in it, so the limit doesn't do anything to it. So that means that we can just copy that first term down again. And now what we are left with is a minus 1 over s minus 4. And again, we can pull that 1 over s minus 4 outside of the limit. And we've got the limit as n goes to infinity of e to the negative. Let's put the s minus 4 first, times n. Okay, so let's have another aside so that we can talk about how to calculate this limit. And so let's think about, let's get rid of this guy. Switch to blue. So let's say we've got we're worrying about the limit as n goes to infinity of e to the negative an. We've got an exponential, but we've got a constant a in front of it. So there's two cases that we're going to worry about here. So if a is positive, then that means we have an exponential decay. So this is n is going that way, and we're going to have our function look like this. So this is e to the negative an. And so if a is positive, then the limit as n goes to infinity of, so as n gets really large, then the exponential is going to get really small, e to the negative an equals 0. Okay, cool. Now, the other case is if a is negative, then that means that our e to the negative an, if a is negative, then that cancels out the negative sign in front of it, and we get exponential growth. Then the limit as n goes to infinity, e to the negative an, you could say it equals infinity, but like for our purposes, The point is that it doesn't exist. It isn't finite. Okay, and so for an integral, we need that limit to be finite in order for us to be able to calculate that integral. So we're going to use both of these answers here as we go back to our problem. So let's think about now the limit that we have to calculate. Well, the s minus 4 is standing in for the a that we had in the blue example. So if s minus 4 is positive, then this limit's going to go to 0. And if s minus 4 is negative, then our limit's going to not exist. This thing's going to blow up. Okay, so let's think about that. Let's just write out some scratch work over here. So if let's think about sort of, okay, let's take our limit and do some scratch work. And this is going to equal 0 if s minus 4 is positive, and that, well, and then it's going to equal infinity if s minus 4 is negative. So we want this case, and another way to write this is that s is greater than 4, okay? So our integral is only going to be defined if s is greater than 4. That means that the domain of our new function, of our Laplace transform, or the answer to our Laplace transform is going to be, it's only going to hold for s greater than 4. So using that scratch work, we know that blah, blah, blah. We know that this thing equals 0 if s is greater than 4. So that means that our answer is going to be all of this stuff right here minus 0 if s is greater than 4. And so then we can just, simplify a tiny bit, and in fact we can copy, and we can say this is equal to this right here. And our domain, we usually sort of put a comma and do our domain s greater than 4. And this is our final answer. So you'll see, if you watch or read some of the examples of the exponential functions or the sine functions, you start doing all of the same computation for all of those over and over. So fortunately in this class, the point isn't really to compute all of these integrals over and over and over again. You should make sure that you understand the details in mathematics and all these examples, but the book very handily has a nice little table. Poof. Oh, we've got all of these different transforms. This is on page 356. And we've got the exponential and polynomials. So exponentials here, polynomials, sine and cosine, and then combinations of those things. And then the last thing that I want to mention is that the first property that falls out from the definition of the Laplace transform is the fact that it's linear. So Laplace transform is linear. And that means that we can write the Laplace transform of the sum of two functions, f1 plus f2, is the sum of the Laplace transform. And it also means that you can pull out a scalar multiple. So the Laplace transform of some constant times a function equals the constant times the Laplace transform of the function. And you can convince yourself of this really easily because the integral operator has this exact same property, that you can split an integral apart from a sum and then pull scalar constants out. And so because you have that property, then that makes it really easy to do a large number of different functions, compute the Laplace transform of them using the table. So what I'm going to do now is move the table down here. And we're going to do one example. We'll keep this over here so that we have it on hand. So I'm going to do an example from the homework. I don't think I actually assigned it, but it's in the book. So this is section 7.2, number 20. And we're asked to compute the Laplace transform of e to the negative 2t cosine square root of 3 times t minus t squared e to the negative 2t. Okay, let's kind of scoot this a little bit smaller. Give ourselves some more space. There we go. So first, using linearity, we can break this up. And so this equals the Laplace transform of e to the negative 2t cosine square root of 3t minus the Laplace transform of t squared e to the negative 2t. So let's worry about the first one first. So in the first one, we can go look for our formula for an exponential times a cosine. And so in this case, we're going to have a will equal negative 2 and b equals square root of 3. And filling in from the table, we get s minus negative 2, so that's s plus 2 over s plus 2 squared plus square root of 3 squared. That equals 3. And our domain here is going to be for s greater than negative 2. And then for our next example, we've got a polynomial times, or not a polynomial, but a power of t times an exponential. So in this case here. And we've got n equals 2, that's the power on t, and a, again, equals negative 2, that's nice. And so we can minus and use the formula. We've got 2 factorial over s plus 2 to the 2 plus 1. And the domain here is going to be for s greater than negative 2. That's convenient that we have the same domain for both parts. If they were different, then we'd have to take the intersection of those two. Whatever s value satisfies both inequalities. But anyway, they're both the same, so now we can just give our answer. Simplified a little bit, we've got s plus 2 over s plus 2 squared plus 3. You can multiply that out if you wanted to, but I don't want to. Minus 2 over s plus 2 cubed, and our domain is all s greater than negative 2, and that is our answer. All right, that's it for section 7.2 that I'm going to do a review on right now. All right, thanks a lot.